Hello everybody, my name is Iman and Esadi. Welcome back to my YouTube channel. Today we're going to go ahead and start chapter 10. Now, in this chapter, we will be discussing radical reactions. We're going to start with an introduction to radicals, and in this introduction, we're going to discuss bond cleavage as well as structure, geometry, stability, and even resonance of radicals. Then we will discuss the 3 phases in a radical mechanism. This is going to include initiation, propagation, and termination. All right, what defines each phase and what kind of patterns do we see in initiation, propagation, and termination? Then we'll define radical initiators and inhibitors before jumping into a discussion about radical halogenation. We will see an example mechanism here for radical chlorination. We will also discuss the selectivity and stereochemistry of halogenation, and we're going to also expand into allylic bromination before wrapping up the chapter by talking about applications and synthesis of radicals. So now that you know the outline of what we're going to cover in this chapter, let's get started. Introducing radicals. Bonds can be broken in one of 2 ways. Heterolytic bond cleavage is where the electrons in a bond are taken by one of the atoms participating in the bond. This is going to result in ion formation as a consequence. We could take a look here. Heterolytic bond cleavage, you have this bond between atom X and Y. When this bond breaks, only one of these atoms is going to take the electrons that make up this bond. That's Y. So Y takes both of the electrons that make up that bond. That results in a negative charge for atom Y, and it results in a positive charge for atom X because atom X has lost an electron total and atom Y has gained an extra electron. Hence the charge associated with X and Y, and how heterolytic bond cleavage results in this ion formation. In homolytic bond cleavage, each atom in the bond gets a single electron. All right, so they share it fairly, and this forms radicals as a consequence. You can think of this as, well, when the bonds break up, what happens? In heterolytic bond cleavage, the wife ends up taking everything. All right. In a homolytic bond cleavage, this couple, they got a prenup, they get what they came in with. All right. And so every atom's electron participating in the bond goes back to that atom. All right. Fantastic. Now, as you notice with homolytic bond cleavage, right here, it's depicted through this single barbed arrow. It's not a full arrow, it's like half an arrow. All right, this is called fishhook, and this shows the motion of one electron. We're going to be using this arrows a lot in our discussion today of radicals, so it's good to make note of it and to understand that a full arrow depicts the movement of 2 electrons, and a half arrow, this fishhook single barbed arrow, depicts the motion of 1 electron. Now, in order to understand the structure and geometry of a radical, let's look first at the geometry of a carbocation versus the geometry of a carboanion. In a carbocation, the carbocation is an sp2 hybridized, and it has a trigonal planar geometry. All right, so it's sp2 hybridized with trigonal planar geometry. A carboanion is going to be sp3 hybridized, and it's going to have a trigonal pyramidal geometry. The difference in geometry obviously results from the difference in the number of non-bonding electrons. A carbon radical is going to be in between these 2 cases in terms of non-bonding electrons. All right, so in a carbocation, all right, we have a carbocation because the carbon has 3 bonds. There's no lone pairs, okay? And it doesn't mean it's octet, hence why it has that positive charge, all right? This is sp2 hybridized. Now, in a carboanion, the carbon has 3 bonds and it has a lone pair, hence the negative charge on there. This is sp3 hybridized. Now, for carbocation, 3 bonds, no lone pairs, which is why it's trigonal planar. Carboanion, 3 bonds, 1 lone pair, all right? Hence why it's trigonal pyramidal. Now, a carbon radical, let's draw this. A carbon radical will be somewhere in between. Carbon has 3 bonds, 1 electron. Not a lone pair, just 1 electron. All right? Now, it's between the 2 cases for carbocation and carboanion in terms of non-bonding electrons. But regardless, what you should know is that it's still treated as a trigonal planar entity. All right, so make sure you note that. Now, the order of stability for carbon radicals follows this hierarchy right here. Now, this is very important to keep in mind. All right, from least stable to most stable, with this end being least stable, this end being most stable, we start off with the Winlich position. Whenever you have a radical at the Winlich position, that means at the location of the double bond, as you see here, this is going to be the least stable form of a carbon radical. Next up is a methyl, all right, then a primary carbon entity, secondary, and then tertiary, where tertiary is the most stable. Now, the reason for this order of carbon radical stability is based on hyperconjugation. Alkyl groups are capable of stabilizing the unpaired electrons through delocalization effects, which is why as you add R groups, whether they be alkyl or acyl groups, to carbon radicals, you result in this higher stability in the carbon radicals. And that is because, again, alkyl groups are capable of stabilizing the unpaired electrons. Now, another thing about radicals is there are several patterns for drawing resonance structures of radicals. The vast majority of situations require only one pattern, and that pattern is characterized by an unpaired electron near a double bond, or a pi bond in general. It can be a triple bond too. So it is characterized, this pattern, by an unpaired electron next to a pi bond. So radicals also participate in resonance, and that is the most common pattern for radical resonance. All right, so what this means is whenever you find the single electron near a double bond, it can participate in resonance, and you can draw the resonance structures. Now, how do you appropriately draw this resonance structure? Well, starting off at the single electron you have, using a fishhook arrow, that electron will come to this bond along with one of the electrons of the double bond. And what happens now is we're going to form a double bond here, as you see. And that means that the other electron of the double bond gets put at the end here. And so that's how you want to draw the resonance structures for carbon radicals. Now, a very important thing to know, and we're going to go back to our hierarchy of carbon radical stability, allylic radical positions. They are in fact more stable than tertiary radicals. So we need to add that to the order of stability we have. Here we have, when we first introduced it, that our tertiary carbon radicals are the most stable. There is one thing that is more stable than a tertiary carbon radical. That is a allylic radical position. All right, so something like this would be more stable than a tertiary carbon radical. All right, now let's do a practice problem or two to get the hang of drawing our fish hook arrows as well as drawing the resonance stabilized structures for radicals. All right, so draw resonance structures for each of the following radicals. We're going to do A. All right, so let's make note. We have a single electron here. It's right next to a double bond. All right, we're going to use fishhook arrows to demonstrate the resonance structures of this molecule right here. Well, if we have an electron right there, this single electron can come here along with one of the electrons of the double bond, and we're going to form a double bond here now. All right, there's still another electron in this double bond. It's going to get dumped on the opposite end. And so what that means is our resonance structure for this molecule is going to look something like this. Fantastic. Let's do B. All right, here's B. Let's draw it out fully. We have our lone electron right here. All right, we want to draw the resonance stabilized structures for this molecule. Here we have our single electron near a double bond. We're going to go ahead and draw that appropriately. The single electron will come here along with one electron from the double bond to form a new double bond here. All right, but there's still a single electron from this double bond. It's going to get dumped right there. What that means is we're going to have a resonance structure that looks like this. All right, well, we're not done yet because look at this. Again, we have a single electron near a double bond. So let's continue to draw all the resonance structures for this molecule. Now, this single electron will come here along with one of the electrons of the pi bond. It's going to form a new double bond there, and that last electron will get dumped here. Fish hook arrows, don't forget. And so we get something that looks like this. Perfect. And this is the resonance structure for molecule B. I'm going to let you attempt C and D. Let me know what you get in the comments below. And if you need help, feel free to reach out to me. But next, what we want to discuss are common patterns in radical reactions. Now, radical reactions go through 3 key phases. The first phase is initiation. Here, there is a net increase in the number of free radicals. This phase is described essentially by the pattern of homolytic cleavage. All right, so initiation implies homolytic cleavage, and here there is going to be a net increase in the number of free radicals. Also note that free radical reactions, they require heat or light to be applied for the homolytic bond cleavage to occur. So in order for initiation, which is the first step of a radical mechanism to occur, we're going to need to have light or heat to make this possible. All right, with light or heat, homolytic cleavage, which is an initiation process, will occur. And homolytic cleavage means that a bond between 2 atoms is going to get broken, where each atom leaves with a single electron, like you see demonstrated here. Fantastic. The second phase of radical mechanisms is propagation. In this step, there's no net gain or loss of free radicals. The common patterns you're going to see in this phase are 1 of 4. All right, 1 of 4. First common pattern you're going to see in the propagation phase is addition to a pi bond, where a radical adds to a pi bond and thereby destroys the pi bond, and in its process generates a new radical. So addition to a pi bond is one common pattern you'll see in propagation. Another common pattern you'll see in propagation is hydrogen abstraction. Here, as the name says, a radical can abstract a hydrogen atom from a compound, and what this is going to do is going to generate a new radical, as you see here. Another thing that can happen, another common pattern in propagation is halogen abstraction. This is just like hydrogen abstraction, but with halogens. So a radical can abstract the halogen atom from a compound and generate a new radical, again, as you see here. And the fourth common pattern you can see during propagation phase is elimination. What happens in elimination is a double bond forms between the alpha and beta position, and the beta position is cleaved, causing the compound to fragment into two pieces. So what you see here, what can happen is this single bond can break off where the atom attached takes one electron, and then this radical electron as well as one electron from this bond gang up to form a double bond. So a double bond is formed between the alpha and beta position, and the beta position is cleaved. Sorry, I drew this wrong. Between the alpha, where the radical is the alpha, and the beta position. All right, where the beta position is cleaved, that means cut off, causing the compound to fragment into two pieces, where you get a double bond for one, and then your X molecule that's attached there leaves as a radical. All right, the last phase is termination. In this step, there is a net decrease in the number of free radicals. So in initiation, there was a net increase. In termination, which is your final step, there is a net decrease in the number of free radicals. And the common pattern you're going to see for this step is coupling. Coupling is when two radicals join together to form a bond. All right, so it's the complete opposite of a homolytic cleavage. All right, you need homolytic cleavage for your initiation phase. All right, you have a bond that breaks. All right, and each molecule gets one of those electrons, right? Like we said, when this bond couple breaks up, all right, they got a prenup, so each one leaves with an electron. This initiates radical mechanisms. What ends it is termination, when the couple gets back together again. All right, and we're going to see this in play, all right, with an example by talking about chlorination of methane. But before we get there, I want to say one thing about this intermediate step, the second phase of radical reactions, which is propagation. Here, you can get several of these occurring where the net reaction of all the steps that might occur during propagation add up to your ultimate reaction goal. And we're going to see that even better when we do chlorination of methane. We're going to do that now. All right, so we have methane. This is what methane looks like. C, which is carbon with 4 hydrogens attached to it. All right, we treat it with Cl2 and some light. All right, and what we get is this gets converted to chloromethane. All right, where we have a hydrogen that is replaced with a chlorine. All right, so when we have methane, we treat it with Cl2 and light. All right, we're going to replace one of the hydrogens with chlorine. How does this happen? Well, first step of a radical reaction is initiation. What happens is initiation is creation of radicals. We're going to need light or heat to promote this step, which we have, and we create chlorine radicals. So our first step is initiation. All right, the Cl2 along with light causes homolytic cleavage, which is our initiation step. Remember, homolytic cleavage is associated with the first step of radical mechanisms, initiation. So our Cl2 is treated with light. All right, it gets homolytically cleaved. What that means is this bond breaks and each chlorine gets an electron. All right, so now we have these chlorine radicals. Fantastic. Now that we've initiated a radical mechanism through homolytic cleavage, we can move on to the second phase of a radical mechanism, which is propagation. Propagation is responsible for the observed reaction, and the sum of each step is going to give the net reaction. that was that last note I made about propagation before we jumped into this example. Propagation, you will see propagation, the patterns, the common patterns you'll see in propagation, remember, is either addition to a pi bond, hydrogen or halogen abstraction, and or elimination. And you can see a good mixture of any of these patterns during propagation. But at the end of the day, propagation is responsible for the observed reaction that we see here, all right? And the sum of each step that occurs in propagation is gonna give the net reaction. So our ultimate reaction is that we want to take methane, convert it to this chloromethane group here. All right, so we start off with methane. We are replacing one of the hydrogens with chlorines. That is ultimately what we're trying to do. So one of the first steps in propagation for chlorination of methane is hydrogen abstraction. Hydrogen abstraction here, a radical, this radical that we formed, this chlorine radical that we have formed, is going to abstract a hydrogen atom from our methane. So when our chlorine radical steals that hydrogen from our methane, we form hydrochloric acid. And now we have carbon with 3 hydrogens only, and of course, 1 single electron. Now what can happen is a halogen abstraction. All right, and now this radical that we formed, this methyl radical that we formed, it can abstract a halogen. It can abstract a halogen, the halogen being chlorine here, all right, and generate a new radical. So with our Cl2 that we have, our methyl radical can steal one of the chlorines from our Cl2, and what we form is the molecule that we want at the end of this, which is a carbon with 3 hydrogens and a chlorine. And again, we have our chlorine radical here. Now, what were we saying about propagation? Well, propagation is responsible for the observed reaction, which means the sum of each step, when we have 2 here, the sum of each step gives the net reaction. So let's look at these 2 steps here, all right, and see what our ultimate net reaction is here. Well, in the hydrogen abstraction step, we have a chlorine radical in the reactants. All right, we have a chlorine radical in our reactants. In the second step, we have a chlorine radical in the products. All right, so these cancel out whenever you add these 2 reactions together. Now, we have a methyl radical in the products of our first step of propagation. We have it in as a reactants in the second step. When we add these 2 reactions together, that cancels out. Look what we have left in the end. In the reactants, we have our methane and our Cl2 when we add these 2 reactions. And in the products, we have our hydrochloric acid and our final product of chloromethane in our products. That is exactly what we want ultimately. So whenever you are writing up the propagation steps for a reaction, make sure that the sum of each step, when you add up all the propagation steps, all right, that at the end, you get your net reaction. All right. Now we can move on to our last final step, which is termination. This involves destroying radicals through coupling. All right, we see in the mechanism that we destroy the 2 chlorine radicals. All right, they add up again through coupling. We destroy them. All right, what other kind of radicals did we have? Well, we destroy 1 methyl radical and 1 chlorine radical to get the final product we want. And also 2 methyl radicals can also couple and destroy that. You can destroy the last 2 methyl radicals as well. So your termination step essentially involves destroying radicals through coupling, and they can react in several ways. And this is the radical mechanism for chlorination of methane. Let's do a practice problem. Make sure we completely understand all the steps of radical mechanism. This question says, draw a mechanism for the following reaction: chlorination of methylene chloride to produce chloroform. All right, so the mechanism is going to have 3 distinct stages. The first stage is going to be initiation. All right, here the chlorine bond is broken to generate chlorine radicals. This step is going to require 2 fishhook arrows. All right, then there are 2 propagation steps, a hydrogen and a halogen abstraction. And then there's going to be our final step, our final phase, which is our termination step. There's going to be a few because there are many radicals that we formed. We're going to couple them together and ultimately destroy our radicals. So let's go ahead and draw this mechanism. Chlorination of methylene chloride. So let's go ahead and draw this. Methylene chloride looks like a carbon with 2 chlorines. All right. Chloroform is going to look like carbon with 3 chlorines attached to it. All right. And we're going to treat this with Cl2 and, of course, some light. All right, so we're going to go from methylene chloride to chloroform through chlorination, which means using Cl2 and light or heat. All right, now I talked you through the steps. We're going to actually draw them out. All right, your first step is initiation. Initiation involves homolytic cleavage. Homolytic cleavage specifically of your Cl2. What's going to happen here is each chlorine gets 1 electron. This is initiated through light or heat. And what you get are 2 chlorine radicals as a consequence of homolytic cleavage of Cl2 initiated by light or heat. Fantastic. That's our first step, initiation. Now, we move on to our second step. Our second step in a radical mechanism is propagation. Propagation. All right, here in propagation, remember, this is going to be the steps that are responsible for our total observed reaction. That means the sum of each step that happens gives the net reaction. Now, this is still a chlorination mechanism. So it's going to follow very similar steps to what we saw for chlorination of methane. This will still abide by the same steps we saw in that example. So for chlorination of methylene chloride to chloroform, we are also in the mechanism going to see for the propagation step hydrogen abstraction and halogen abstraction. So we're going to go ahead and we're going to draw that. All right. Now, starting with methylene chloride. All right. Our first step is going to be hydrogen abstraction. All right. So our chlorine radical and the hydrogen of our methylene chloride, all right, they're going to form a bond. So we're going to take one of the electrons of our radical and one of the electrons for this bond between carbon and hydrogen. All right. And that means that the other electron gets left behind for the carbon. What we get is a radical. All right. This radical right here and hydrochloric acid. This is for hydrogen abstraction. All right. The next step is halogen abstraction. So we take this radical that we formed in our last step, and it can react with Cl2 that we had to begin with. Now, this electron from the carbon and a single electron from the chlorine-chlorine bond are going to form a new bond between this carbon and chlorine, and this last electron from the bond gets left behind to the chlorine. All right, this is halogen abstraction. What we get here is our chloroform. All right, what we get is our chloroform and a chlorine radical. Fantastic. Now, let's look at the net reaction of these two steps. If we added both of these steps, well, in one step, we have chlorine in the reactants and chlorine in the products. When you add these two reactions together, those cancel out. Fantastic. Now, we have this radical and in the products of one and as the reactants of another, and so those cancel out. What we are left with in the reactant side then is the methylene chloride we started off with and Cl2, this part of the reaction, and for our products we have our chloroform and hydrochloric acid, all right, which is this part of the reaction. That's fantastic. That's exactly what we wanted to get. This is the net reaction we're looking for. So we've appropriately written the propagation steps for this reaction. Now, last but not least is termination. All right, so now your radicals can be coupled together to destroy each other. All right, and so we have no room here. I'm just gonna erase our initiation and write our termination here. All right, so our last step is termination. And so our radicals can couple together to destroy each other. So two chlorine radicals can react with each other like we saw in our example here. All right, they can couple to form Cl2. Also, we can couple our, there's no room here. We can also couple ClH, this radical that we formed in our propagation step, with a chlorine radical, ultimately, all right, to form our chloroform, and thereby destroying more radicals in our termination step. Fantastic. All right, that is all for today. Next time, we're going to go ahead and finish the rest of Chapter 10. If you have any questions, leave them in the comments or reach out to me personally. I'd be more than happy to help. If you want to see more practice problems for the topics that we've covered today, let me know. I'd be more than happy to accommodate that. Other than that, good luck, happy studying, and have a beautiful day.